breaking the wall to the early universe. What the James Webb Space Telescope can tell us about our origins. Jeyhan Kartaltepe, Rochester Institute of Technology.
On November 9th, 1989, I was 8 years old and starting to learn about the wonders of space.
It's very exciting to be here and get to tell you all about the James Webb Space Telescope. It launched in December and has just started taking its first observations this past summer. I'm an astronomer, and I work on galaxies in the early universe. And I am leading several different analyses as a user of JWST. One of the things that really brought me into this field was the idea that I could connect my day-to-day work with the big philosophical questions that it's connected to. Why are we here? Where did we come from? How did our planet, our sun, our galaxy, how did they arise? How did they form? I think humanity has always wondered about these deep questions and has always had a curiosity to know how we fit in with the larger universe. I think a project like JWST really embodies this sense of wonder and curiosity that people have. People from all over the world had to work together for many years to make JWST a reality. They had to work through many different delays and problems. They had to work through a global pandemic. And overall, it has been a resounding success. This talk is about breaking the wall to the early universe, but it's also about breaking the wall to how people can achieve great things if they just work together. This video shows a cosmological simulation of what we think the universe looks like on very large scales. The color in this video shows different physical aspects. So at first it's blue, highlighting dark matter in the universe, and you'll see different colors appear as the video progresses that highlight gas in the universe at different temperatures. In the very early universe, material was overall uniform, but there were very slight clumps of material that started to come together under the influence of gravity. And it's these clumps that eventually formed the seeds that become galaxies and galaxy clusters that we see in this simulation. What you see here, this structure is made up of many, many galaxies all throughout. These galaxies aren't isolated. They live in a large galactic ecosystem, and gas is moving between and through all of these galaxies through things like interactions, through supernovae explosions, and through processes of their central supermassive black holes. So when a telescope looks out into the universe, it's seeing not only objects that are nearby, it's seeing objects that are very distant from us. Because the speed of light is finite, it takes time for light to reach us from the distant universe. It takes light 8 minutes to reach us from the sun, years for the nearest galaxies, years for the nearest stars, millions of years for the nearest galaxies, and billions of years for the most distant ones. This means that using a telescope is like having a time machine where we can look back into the past and see galaxies as they were all throughout cosmic history. A lot of people think of JWST as a successor to Hubble. Hubble has become a household name. Everyone knows about it, has seen images from it. But I also think of JWST as being a successor to Spitzer, which is a telescope that's no longer operational, but observed in the infrared part of the spectrum. This image shows the difference between these three different telescopes. And the biggest difference you might notice is the size of their mirror. JWST has a very large mirror, and that is what gives it so much power over these other telescopes. JWST is also optimized to observe in the infrared part of the spectrum, which is why it has this gold plating. So what's so important about the infrared? Well, dust in galaxies absorbs UV and optical light and re-emits some of that energy into the infrared part of the spectrum. So some galaxies are really bright in the infrared, and we can learn a lot about them by studying them in this part of the spectrum. Also, because of the expansion of the universe, light from galaxies actually shifts towards the red part of the spectrum. So galaxies in the very distant universe that emit visible light, we actually observe that light in the infrared. So JWST has a long story of how it came to be, and its design was really motivated by the key science questions that astronomers wanted to ask, including how the first galaxies actually formed. And so all of these science questions led to the initial design of what it looks like. And for such an ambitious project like this, there are always technical challenges. And so one of these technical challenges is, if we want to observe very distant galaxies, we need a really big mirror because we want to collect a lot of light to see faint things. But you have to take that big mirror and somehow get it up into space. So the solution was to design a mirror that is segmented and foldable so that it could fit in existing launch vehicles. Another challenge is that we want to observe in the infrared. Well, to observe in the infrared, the telescope and its instrumentation has to be kept very, very cold. This is because warm things emit in the infrared, and that can provide a source of background noise in your images, which you don't want. So the solution to this was to send the telescope very far from Earth. It's over 1.5 million kilometers away. And also to add this sun shield. So this sun shield at all times sits in between the telescope itself and the sun, protecting it from the sun's heat. This also had to be cinched up so that the entire thing could fit inside the launch vehicle. So now that JWST is up in space, what can we actually learn? Well, we're going to learn about the very beginnings of our universe by studying the light from the first stars and galaxies that ever formed. This shows the timeline since the Big Bang, with the present day on the left and the Big Bang itself off to the right. In red, you see the redshift that corresponds to that time. Redshift of a galaxy is a measure of its distance. The farther away a galaxy is, the higher its redshift is, and the further back in time we are seeing. Over the past few decades, we have pushed our cosmic frontier to observe galaxies at greater and greater distances. And until recently, Hubble has held the record. But now, JWST is able to observe galaxies all the way out to a period just a couple 100 million years after the Big Bang. And it's during this time period that these first structures were beginning to form and be put into place. We can also learn about how galaxies formed, evolved, and changed over the age of the universe. This image on the left shows the initial classification scheme of galaxies that was proposed by Edwin Hubble 100 years ago. Galaxies nearby us fall into two different main categories. They can be disk galaxies with spiral arms, or they can be more rounded and elliptical in appearance. The Hubble Space Telescope has shown us that the underpinnings of these basic shapes were already in place at least 11 billion years ago. We need JWST to look even further back to tell us how galaxies like our own Milky Way actually formed. So one of the big open questions is, how early in the very beginning of the universe were those first disks able to form and be stable? This image shows a comparison of simulated objects between the different telescopes, so you can see the details that we can see with JWST. At the top is Spitzer, is a comparison with Spitzer at the same infrared wavelengths, and on the bottom is a comparison with Hubble. Notice the difference with the size of the telescope, from the smallest Spitzer to the largest JWST. JWST is really bringing the details of galaxy shapes into focus. So those were simulated images, but I think we all want to see what real images look like. And so many of you may have seen this great press release image that came out this summer after the first data were released. This is an image of a galaxy cluster in comparison to an image that was taken with Hubble years before. And you can see the stark difference between the two. There are many more galaxies that are visible in the JWST image, and if you could zoom in on all of them, you'd be able to see the rich detail and structure that we haven't been able to see before. So I am working with a survey called SEERS. This is a program that was designed to test out the different instrument modes of JWST in its first months of observations. We observed 4 different pointings with the near-infrared camera on JWST this past summer, and since then we've been working really hard to analyze this data. In fact, we just had our first public release of images just this week, and so everybody can download and play around with that data. This is an image of us looking at all of these galaxies on this gigantic screen so we could look at all of this rich detail. So the top of this image shows our full data set, all the way zoomed out. And every tiny speck you can see in this image is a galaxy, and there are thousands of them. I'm only going to focus on one, and that's the one that's zoomed in that you see here on the bottom right. This is a galaxy at a redshift of 12, which means we're seeing it at 300 million years after the Big Bang. Notice how red it is, right? That's the power of JWST. And our first publication from this data was based on this galaxy because it was our most robust candidate for something in the early universe, though now we have many more. So it's only been a couple of months, and we're hard at work analyzing this data, and so more results are going to come, but I'd like to highlight a couple of surprising initial findings. We are finding more bright galaxies in the early universe than we initially expected. So this is currently challenging our theoretical models. We are also finding that galaxies in the early universe have a broad diversity of shapes and structures. Here are some examples that are at very great distances from us. At this time, we're already seeing galaxies that have these disk structures in them. So we haven't yet reached that period of time where the first disks were able to form. So more work is going to need to be done for that. So this brings me to the project that's the nearest and dearest to my heart, and that's the Cosmos Webb survey. Cosmos Webb was selected as the largest program that JWST is going to observe during its first year. In over 254 hours, we are going to observe one part of the sky in a region known as the Cosmos Field. What makes this program unique is that we're going to observe a large area with no gaps at all. So this is illustrated on this figure here, where the background grayscale image shows the previous existing Hubble data, and the area we're going to observe with the near-infrared camera is shown in the blue box, along with the full moon. So if you can picture the full moon on the night sky, that helps to give you a sense of the wide area that we're going to cover. At the same time, we're going to be able to get mid-infrared imaging shown in these red stripes. Now, to motivate why we would want to cover such a large area, think back to the initial video I showed you of the cosmological simulation. We would like to not only find galaxies in the early universe, but we would like to place them in their broader environmental context. We want to understand if galaxies that live in really dense environments, like cities, are different from those that live in the more filamentary, isolated structures, like things out in the suburbs, or how different they are from galaxies that are even more isolated or out in the country. And so we really need this wide area to be able to map out all of these large structures. So when we were first told that we were getting awarded this telescope time, our whole team was in complete shock. And if I'm honest with you, I think we still are. I think it hasn't quite set in. And that's because this was such a huge ask. Asking for 255 hours was completely ambitious, and it's something that nobody thought JWST would do in its first year, that it wouldn't even happen. But we decided to do it anyway. It was an important project, and we all felt deeply about it. And we're going to be getting our first data starting in December. So I've given you a taste today of some of the first things we're learning from JWST, but it's only been a couple of months. Projects like Cosmos Webb and others are going to be finding many thousands of galaxies in the very early universe. And I personally can't wait to see the discoveries that unfold over the next few years. Thank you very much for your time.